So we've always treated gravity in these problems as being constant, because it doesn't change very much. And what value do we give to gravity on the surface of the Earth? 9.80 meters per second squared, and it doesn't change from that, right? Okay, but would you agree that if we were to talk about, on a larger scale, if we were to talk about gravitational field strength, it would change if maybe we went 40,000 miles away from the surface of the Earth? Would we expect gravity to be different? Well, yeah, quite a bit.
What about on the top of Mount Everest?
Even there, you're only up just under 30,000 feet, and so no, not appreciably. And to compound that, you're standing on top of a mountain, and so the additional mass in that conical mountain probably offsets it a little bit anyway, and so it probably didn't change appreciably at all. Yeah.
Yeah.
Okay, you'll think of it. Okay, so there is a. Remember?
I knew these.
No, I didn't. Is there a way to is there a formula to calculate what the force of gravity will be based on the mass of the object?
Yeah, mass of the two objects.
Yeah, like the mass of the Earth, but wouldn't you also need like area or radius or something?
Yeah, you would. This is the equation. I'll give it to you.
Oh.
I mean, you don't have to write this down. We'll talk more about this later.
You just know what I'm talking about.
Oh yeah.
You did go to school.
Yeah. It's not like these.
That's it. Simple. That's the law of universal gravitation.
What's the G?
Okay, the capital G is the universal gravitation constant.
Which is
It's something like 6.67 times 10 to the negative 34. So it's just a really, really tiny number, super small, which speaks to what a wimpy force gravity is compared to the other forces. It's really a weak force. So tiny little constant. What's the M1 and the M2? What do you suppose they represent? Yeah, the masses of the two objects. So for example, if we want to do this for like the mass of somebody or something on the surface of the Earth and the mass of the Earth, we could change this to look like the mass of the object times the mass of the Earth.
Yeah.
And what do you think the R stands for?
Radius.
Well, okay, it stands for the distance between the centers of mass of the two objects. So for a person standing on the Earth, that's essentially just the radius of the Earth, isn't it?
So if there's no distance between the two objects and there's no gravity, there's no force of gravity?
No, we'll talk about that. Hold that thought. So then, how could we calculate G? What is G equal to?
That.
Because this has to equal the mass of the object times G. So wouldn't G have to just be the product of all
Yeah.
that stuff? It is. Okay? The pseudo constant small g, the sort of constant of the acceleration of gravity on the surface of the Earth is really just the product of the universal gravitation constant times the very large mass of the Earth divided by the radius of the Earth in standard units.
Do we really have like a good estimate of the mass of the Earth?
Yeah, we can.
Oh, yeah, I guess you can easily.
Well, we can weigh it. We could weigh it in this classroom. We could indirectly weigh it, and I'm not going to talk about that today, but hold that thought, because we'll talk about how we could do it. It's really not hard to do. We could do it. Just an accurate balance. That's all it takes. We could mass the Earth.
Just turn it upside down.
Yeah, let's turn it upside down. There you go. Okay, so what does this tell us, though? So for any two objects, like let's just say we're going to take two objects in outer space. If we want to calculate the gravitational force between them, well, capital G is a constant. Are the masses of the objects going to change? No, they're going to stay the same, aren't they? So really then the gravitational force is proportional to 1 over r squared. So we say that it is an inverse square law. If I double my distance away from the center of the Earth, what happens to the gravitational strength, the strength of the field, my weight? Gets cut by a factor of 4, right? Does that make sense? Because I'm going to double the distance from the center, but then that amount gets squared, so it's actually going to increase the denominator by a factor of 4, which decreases the fraction by a factor of 4, right?
Yeah.
Get the idea? Okay. right, so that has some implications. Let's say two interesting things. Let's take two kind of thought experiments here. Let's say that we first of all take the Earth and we compress it. Okay, which, we compress it, so we make the matter into some type of exotic matter, which exists in the universe that's extremely dense, much, much denser than the densest normal matter on the planet, which would be lead. So it's denser than that. Let's say we make the radius, I don't know, how about if we just make it like, let's say 1/5 of its current radius. So we'll compact it quite a bit. So the new radius is 5 times as small as the current radius. What's that going to do to your weight?
Increase
By how much?
by, you said 1/5?
Yep.
So then it'll be 1/20.
Okay, so if I change the radius from its current radius, like let's say currently it's r sub e for the mass of the Earth. Okay.
By 20.
25 times greater.
Right, okay, so if I change that, so the new radius is going to be 1/5 of the Earth's radius. So then it's going to become my new, call it Fg prime, is going to be equal to, or is going to be proportional to, let's just do it that way. We could also just write this as, instead of using proportionality symbol, we'll just lump all this other stuff into one big constant. Does that make sense? Like the g times the product of the masses, we'll just call that k. So it's really just k over the radius of the Earth squared. The k is not going to change, regardless of what we do, right? Because we're not changing the mass of the Earth, just its radius. So the new one then is going to equal k over the radius of the Earth over 5 squared, which is the same thing as k over the radius of the Earth squared over 25, and we divide by a fraction, we flip and multiply. So do you see that it's actually equal to 25 times k over the radius of the Earth squared, which was the original gravitational strength? Okay, so if we decrease the radius by a factor of 5, our weight would increase by a factor of 25, and we would die. Because you couldn't, so we'll load a 200-pound person would then weigh 5,000 pounds.
Oh.
Okay, that would be, actually, that would be more than that. That's right, 200-pound person would weigh 5,000 pounds. You couldn't support that. You couldn't breathe. Your organs would probably squish themselves. You'd have some problems. Your skeleton would break. You couldn't survive, right? So that would be a bad thing to do. Let's not compress the
So
Earth.
we're at the perfect.
For us, we are.
We are evolved to.
Exactly. It's perfect for us because we've adapted for it to work pretty well for us. Now, what do you think would happen? Let's do an even weirder thing. Let's take the Earth and let's compress it again, but this time we're going to compress it from the inside out. So we're going to take, here's the outside of the Earth. We're going to start in the middle, and we're just going to push all the guts of the Earth, the core and all that stuff. We're just going to squish them up against the crust so that we end up with this really hard, dense crust of the Earth that's the same radius as before, but it's hollow in the middle. See what I'm saying?
Yeah.
Okay, so we redistributed this ultra-dense matter so it looks like this now.
Make it nice and sphere.
Yeah, so the inside is all completely hollowed out. Okay, from the outside, are you going to know any different? No, not going to know any different at all. You could, if you were approaching in a spacecraft, the Earth still has the same mass, and if we go back to these equations, the other thing you need to know about gravity is the gravitational field is calculated from the center of mass of the object. So from the outside, it doesn't matter how the mass is distributed at all. As long as the center of mass stays in the same place, the field looks identical. Okay? So we can't tell the difference. We could stand on the surface of this and it would be identical. But let's say that we carve a tunnel through this into the inside. What do you think happens as soon as we poke our head out of this tunnel down here?
You fall into the center.
Fall into the center and just oscillate back and forth?
No, you
I think you just lost.
Get
You go.
crushed.
Here's what happens. If you, let's say it's got one of those ladders that you can kind of climb down, you know, those circular ladders, it's
It's
got
a
rungs on it.
block.
So you climb down that thing and then you kind of suspend yourself on the inside and let go. And nothing happens. You float.
Ah, I was right.
You float.
At
Turns
any
out
point,
there would be 0 G inside of this shell.
anywhere.
Anywhere inside the shell. And that's, if you go on and study physics in college, you'll probably solve that problem. You just take a 3-dimensional integral. It's not a hard thing to do. You just add up the gravitational contributions of all the little pieces of the Earth, and you divide it up in a convenient way. You divide it up into little spherical, what you take are little, the pieces would look like little, on the top they would look square. How do I explain this? Like if you took a square on the top, but then the lines that define the side of the cut go towards the center of the Earth, it'd be like taking out a square divot. If it went all the way to the Earth, it would come to a point. You know what I mean? Only they're infinitesimally small. In calculus, that's all you ever deal with, infinitesimally small elements, right? And we'll get to that. That's coming up. That's our next topic after chapter 3 in 2 dimensions.
So
Okay.
does that mean that like theoretically that shape could be like a viable form of a planet?
Well, no, because it couldn't support itself. But it could never exist, but if it did, what you'd find is that the gravitational field inside is 0. And why would it be? This is what's kind of interesting. If you take any point on the inside and you add up the gravitational contributions, what you find is that there's a whole bunch of parts of this, and keep in mind this is like a cross section, so it's spherical, right? But like this whole region up here, pretty close to it, so you'd think that should win probably, right? Because it's so close that the gravitational field is going to be much stronger.
Yeah.
Okay, but thing is, all this other part down here that's further away, there's a lot more of it, and they exactly balance out all the time, turns out. And so inside, you have the net contribution is the net force is 0. Okay, so then let's combine those two thoughts. And let's look at the situation where now we're going to do something tricky. Now we're going to do something that's maybe more conceivable here. We're not going to do any compressing. This time we're just going to start at the surface and we're just going to carve out a tunnel straight down to the core, and we're going to line this with Coulium insulation, which we get at the Acme store, just like Sliprium, and it's infinitely thermally insulated. So it'll keep you cool in any situation. So even though we're going to be going through the molten hot core of the Earth, the Coulium line tunnel will keep us just at normal room temperature. Okay. It's expensive.
Why don't they do that?
Well, it's really expensive.
Don't you see the GM?
Trademark, yeah.
Otherwise, it would be.
It's Acme. So we go down the center of this thing. Now I want you to predict for me what's going to happen as you get closer to the center of this thing. Are you going to survive?
No.
Okay, why wouldn't you survive?
What? You'll get squished.
You get squished because the radius gets so small, right?
No, you're tricking me. I don't believe
You
you.
can tell.
You have the other mass
Yeah.
on the other side.
Okay, you would survive. In fact, as you walk down towards the center,
You'll float.
you're actually, every step you
Every
take,
time. Float.
every step you take, you're going to get a little bit lighter.
Ah,
But you don't,
When
until
you
at the
don't
very
see it
center, if it was
float.
carved out, you'd float. But as you move towards the center, yeah, every step that you take is going to get you a little bit less. The field's going to drop off a little bit. How come?
blows away.
How come? Like if you were right here, for example, I think it's going to be linear. Yeah, it would be. So when you're right here, your mass or your weight would only be half as great as it was at the surface. How come?
Catching up to the center.
Okay, but being that much closer to the center, if I'm halfway there, theoretically, I should weigh 8 times as much,
Yeah,
right?
Yeah.
Because look at our
equation.
right? If that's half as big, I should weigh 4 times as much. Sorry. How come?
Is it because it's big?
No.
Because there's not another open tube on the other side.
Because you have the mass on the other side.
Okay, because of Because of this, right? Every time I move down through the earth and I get closer to the center, all of the earth, that shell of the planet that's further away from the center than I am, makes no gravitational contribution, right? See what I'm saying? It's like I'm climbing through the concentric layers of the earth, like layers of the onion, and all the layers that are further away, they don't matter, right? See what I'm saying? So then, right here, all this stuff out here that's further away, so everything out there doesn't make a difference. Only the part that's inside of where I'm standing makes a contribution, right?
Are you
Okay.
still talking about the core being pushed outside of the crust?
No, now it's just a normal earth,
Okay.
but we just carved a tunnel down here. Okay? Okay, so but now think about this. So as I get closer to the center, think about the amount of volume, how the volume changes, right? The volume of a sphere is 4/3 pi r cubed, right? So if I'm halfway to the center of the earth, wouldn't you agree then that the volume that remains there is only 1/8 of the volume that I started with? Right? Do you get that? Because volume of a sphere is 4/3 pi r cubed, right? 4/3, my pen went out there. 4/3 pi r cubed, right?
Yes.
So if I cut r in half, I'm actually decreasing the total volume by a factor of 8,
Yes.
right? Okay, what's happening to the gravitational strength? The gravitational strength is only increasing by a factor of 4. You get it?
Yes.
Because I'm getting closer to the center, but there's only 1/8 as much matter. And so I actually am losing volume at a rate that's greater than the rate at which my gravitational field is increasing. And so I lose weight, right? When I'm halfway there, I only weigh half as much. Interesting, huh? Just in case. Never know when you might make this trip. You gotta know what to expect.
We could live it,
Yeah.
apparently.
So anyway, so this is our kind of our conventional Newtonian classical explanation of gravity. It works really well. It works for almost everything we need it to do. If we want to talk about like the orbital mechanics of a satellite, we don't need anything fancy. All we need is that equation. That's it. And a little calculus, and we got it done. Right? We know that if this is the Earth, and I've got some satellite up here that's traveling tangentially at just the right speed, it's going to be in uniform circular motion, right? If we get it going just the right speed, then the gravitational force, the weight of the satellite, will provide the centripetal force that keeps it moving in a circle, and it'll just stay there indefinitely. It actually won't stay there indefinitely. There is a little bit of tenuous dust and gas around even up far away from the Earth, and with time it'll run into that and it'll degrade its orbit a little bit, but a long time. I mean, it'll stay there a long, long time without changing its radius appreciably at all. What would you have to do if you wanted this satellite to go back to Earth? In what direction would you fire the retro rockets on the satellite?
What do you mean?
If I want to go to Earth and I'm traveling in that direction.
Kind of gave it away when you said retro.
Well, I mean, there are rockets pointing in all directions on this thing, let's say. I can fire in any direction. I can fire the burners in any direction I want to provide thrust in any direction. What am I going to do?
Towards the Earth.
Towards the Earth?
Yeah. It's a trick question. You can tell. Too easy to say that.
If I fire it towards the Earth, then, okay, opposite direction I'm going.
Yeah.
Okay, how about that? So if I fire them,
Oh, I thought that meant toward the Earth.
so if I fire them
The
forward, like
fire is going.
fire them forward in the direction I'm traveling, what's that going to do? It's going to slow me down, right? Now we know that centripetal acceleration equals v squared over r, right? And so what's that gonna do? If I keep the radius the same, but I reduce my speed, that's reducing the amount of centripetal acceleration necessary to keep me moving in a circle, right? But is gravity gonna change? No, gravity's gonna stay the same. And so now all of a sudden, the acceleration of gravity is gonna be more than I need to keep in a circle, and it's gonna cause me to spiral into the planet.
Isn't that
Right.
what we want?
That's what we wanted. That was a good idea. Okay, a lot of times people would say something different than that. They would say that maybe you want to fire the rockets like this to push you towards Earth. Okay, but is that changing your speed at all? It's not. It's not changing your speed. And so what's really going to happen there is not what you want. What's going to happen there is it's maybe going to deviate, you're going to deviate from a uniform circular motion, but likely what's going to happen is just going to end up in an eccentric ellipse. So you end up doing something like that instead, but you still stay in orbit, right?
What would happen if you fired them at like an angle?
Well, if you fire them at an angle, then you're going to change your velocity too, right? Like if I were to fire them backwards like that, then I'm going to pick up speed, and I might actually leave orbit, right? If I get them going fast enough, this ellipse is going to cross the intermediate path of a hyperbola and end up as a it's going to eventually get to a point where it's parabolic, and it'll do this then. When it's parabolic, it'll just go through.
How do you know that?
Well, because this is one of the things we'll talk about, because the three possible orbital trajectories of anything that's gravitationally attracted to another body, if it's a closed orbit, it's an ellipse. If it's an open orbit, where as it continues away, as time approaches infinity, it will still carry speed with it, would be a hyperbola. And then a parabola, an interesting way of thinking about it, a parabola is really just an infinitely large ellipse, because the in-between would be a parabola. And then as time approaches infinity, the object would approach zero speed, but it would never come back. You see, and so really that's all a parabola. Honestly, it's an interesting way to think about it is, it's just a part of an infinitely large ellipse. Whereas a hyperbola is different. Hyperbola has a different look to it. A hyperbola looks like that. Okay, and we'll get to those. Later in math you'll talk about. Those are conic sections and analytic geometry. You guys will talk about that later in math. But yeah.
What would happen if you fired like at an angle between the two? Until you already written down.
The two of, well, yeah. Then you would be like if you fired at, say, like this direction,
No, thinking the other.
like that way.
No,
That way. Okay. Oh, that way. Okay. So if you fired that way, it depends. It could either be an ellipse or it could end up being. Could be any of them. It just depends. Just depends. Just depends.
Oh, I think that's
What's that?
the person needed to
Could be a hyperbola. Could be a parabola, or it could be an ellipse. Depends on how strongly you fire it. Okay. All right. But what I want to talk about today, I kind of want to get us thinking about, is something a little bit different. So I told you that using the laws of universal gravitation, we can write relatively simple computer programs that they're called Monte Carlo simulations, and they can predict with really, really astounding accuracy where an object is going to be at any point in time. Like, for example, we could do this calculation now with just a little bit of extra calculus. We could predict, for example, where the planet Mars is going to be on a specific second in, who knows, when you're 50 years old. And it would be really accurate. It's only going to vary from that by just ever so slightly. I mean, insignificant amounts. So it would be very, very accurate. So when astronauts, when they make these calculations about you know, how to hit the moon or how to hit. They're not doing anything fancy. They're just using these. They don't have to. They can use this basic, straightforward physics, and that works really, really well. People have known about this for a long time. Even long before we sent people to the moon, we were able to make stellar predictions, or at least in our solar system, predictions about where the planets were going to be. People did that a long time ago, very accurately. But it didn't work for one planet. It didn't work for Mercury. Mercury is not where it's supposed to be, ever. You can calculate where it's supposed to be, but it doesn't end up there. If you do the physics, because we know how massive it is, we know what its radius from the sun is, we know how fast it's going. You should be able to predict, based on those parameters, exactly where it's going to be, but it always ends up being a little bit behind where it's supposed to be. How come? It's perplexed people.
That equation was kind of-
Because it's so
There's
close
the
to
general
the sun.
equation we use is
Okay.
a precise amount.
It has to do with the fact that it's close to the sun. The reason it only happens to Mercury is because Mercury is the closest planet to the sun. Now this was, you know, if you go back over 100 years ago, people were having this discussion and physicists were coming up with just the weirdest possible explanations for why this could be the case. I mean, stuff that now you just seems laughable.
Like what?
But then this one dude came up with a pretty good explanation.
And stuff.
Yeah. And he was just about laughed out of the room when he came up with this explanation. But when people tested it, it worked. And it predicted where Mercury was supposed to be. And then people kind of started to listen to this crackpot a little bit. And the rest is history. Okay, Einstein told us some weird stuff though. Why does this pen drop?
Gravity.
Gravity, of course, right? Well, what's that?
Interaction between two objects.
Traction between two objects. What kind of a, so how would you categorize it then? It's a what?
Force.
It's a force, sure, it's a force. Well, there you go. Well, why? What causes it?
Do people put this?
Yeah, I'm gonna tell you the answer to it. We know that, we actually know the answer. We know the answer, and this is one of the most tested theories. And when I say theory, we gotta understand something about theories. In science, when you say a theory, it doesn't mean what people on the street think theory means. People associate the word theory with hypothesis. Like, no, I have a theory. I have a theory why TJ was late yesterday. What I really mean is I have a hypothesis about why he was late yesterday. I don't, it's not a theory.
would describe that as
Yeah, theory in math, or in science, or math for that matter, a theory is really just a body of working knowledge that is always growing. That's, a theory is a big thing. Like we talk about the theory of gravity. It's not, think it's gonna fall? I don't know. It's gonna fall every time. Gravity's real. We know it's gonna fall every time I drop it. It's not a hypothesis. The theory of gravity just has to do with all of the compilation of all we know about gravity, mathematically and otherwise, right? So, where was I going with that? I kind of lost track. Oh yeah, so, okay, so when we drop this thing, you're not telling me why. You're telling me, I mean, you might even give me an equation, right? But that still isn't telling me why. It's telling me very accurately how it's going to happen. It's making a prediction, but it says nothing about the cause. What's the cause?
Aristotle would say they want to be together.
Aristotle would say something weird like that, like objects want to be together or something, as if they had an opinion on the matter. But it's not that either, I promise you. What's really happening is, and this is going to sound weird, but this is the absolute truth. This I can say with absolute certainty. This pen is falling into a gravitational well. It is. It is. I can even say something weirder than that. I could say that actually it is not doing anything weird. We are. By standing on the surface of the earth, we are being accelerated. We are not traveling a direct line through space-time, but the pen is. The pen is stationary in space-time. We're not. We're not, because the floor is pushing on us and accelerating us. Okay? But that's a little bit, we'll get to maybe that one a little bit later. But for now, let's just focus on the idea that this really is falling into a higher dimensional gravity well. It's a little bit of an oversimplification, but we could say, for all intents and purposes, that it's falling into a four-dimensional gravity well. And it really is doing that. Okay, so why don't we see the well? We don't see the well because it would require us to be able to perceive the other dimension, the extra dimension, and we can't because we are in the three-dimensional prison. We're in a universe that only has 3 extended dimensions, and so we can't see that warping. Okay, does that make sense?
Like waves?
Well, I mean, kind of. Here's a way to think about this. We have to agree on just a couple little things. I'm not going to get very far with this today, but would you agree with me that people, when we see things, the world around us, what we're really doing is we're perceiving it in 2 dimensions. Our eyes take 2-dimensional pictures, which we can string together. We play some tricks. We have 2 of these visual organs that allow us to triangulate, and that helps us to be able to conceive of depth, right? We can perceive that there's going to be some depth there. I noticed that if I'm walking across the front of the room, I see that Nicole is going to cross my field of vision faster than Matthew is. How come? She's a lot closer. So my brain latches onto that and says, oh, she's close. Yeah, that's what it is. That's all it is. If I walk over this way a little bit, I see that TJ disappears. Oh, is he gone? No, he's not gone. He's just behind. He's behind. I know about behind, right? Okay. He's not gone. He's there. I panicked for a second. I forgot about behindness, but he's there. We can. We only perceive 2 dimensions, but we can stitch these together with time, and we have a strong conception that we live in a 3-dimensional universe. We can conceive of that very easily and build mental models for that, right? And so we get that there's left, right, up, down, and front, back, right? We understand all those things well.
Do the other 3 forces work in like 4 dimensions?
Well,
More
it's
or less, or-
it's not exactly. It's a little different. It's a little different. Gravity's unique. Okay, I need to introduce you to some of my buddies here that you may not have known about. It turns out that my whiteboard is actually a small piece of an infinite 2-dimensional universe, which I affectionately call Flatland.
Oh,
And these guys, here's Mr. Blue and Mr. Orange and Miss Scarlet here. They are just these friendly, nice folks, but they're Flatlanders. Their universe is very different than ours. It has 2 dimensions, right? So their universe, they perceive things, they perceive things much differently than we do, right? As far as we're concerned, if we want to have kind of a common language here, we could say that they understand left, right, front, back, or up, down, but not front, back. Front, back is like, what? What are those weird words? I don't understand that at all, right? Doesn't make any sense. In their universe, they're smart. They do flat math, and they know that in their 2-dimensional universe, they have room for exactly 2 orthogonal axes, right? They can draw. They have 2 lines at right angles to each other, and they get that. But to them, the idea of an extra dimension, like a 3rd dimension, whoa, how can that be? There's no way they could fit 3 vectors that would all be at right angles to each other in their flat universe. Now we can, right? We can add an extra dimension, the z dimension, that we can't even describe that to them. They have no idea what that could possibly be like. And there's no vocabulary we could ever use to describe that to them. But when we talk to these guys and we say, oh yeah, we see you only got 2, but we actually have room in our universe for a 3rd, and they're just thinking, wow, how lucky. Where could that go? They have no idea. But for us, it'd be like us talking to 4th dimensioners, and they'd be having the same conversation with us. They'd be saying, you guys, 3 right angle dimensions, 3 orthogonal dimensions. We got 4. Don't you get it? It's theirs is there other, who knows, what would they call it? I don't know. Maybe they call it blah and fork or something. I don't know. We don't know what it is, but
You can only have 3 because you
they've
can't
got
go
some other
beyond.
words that we don't understand that have to do with the really obvious other direction that they can travel that we just can't conceive of. What was
We know there's only 3 because you can't go beyond Z.
right? That's all we have room for is the Z, right? So they must have they've got some other. They must have started theirs
They
with
just have a longer
W.
alphabet.
They started theirs with
Yeah,
W.
they have a 27.
Yeah, maybe they do. There you go. But theirs is a different place. Now, the last thing I want to leave you with here, and this is, we'll have to kind of, the goal is going to be for us to take this flatland universe, and we're going to try to build a model that we could visualize, right? Build a model that's obvious to us that would simulate gravity in their flat universe. But then we have the benefit of being able to kind of visualize the work, right? Before we do that, though, just I want you to kind of understand the limitations of our ability to understand their universe, right? Now, think about, we might try to say, okay, well, we're going to immerse ourselves in flatland. That might mean we kind of stick our head into the board until our eyes are just, inside this plane, our eyeballs, right? What would it look like to us then, maybe?
Lines.
Yeah, okay, so we would just see their entire universe would just be a white horizon, just a white line, right? Does that make sense?
We could still go forward.
Okay, and well, we could, that would kind of be like them, and then what would Miss Scarlett look like if I stuck my head in there? She'd look like just a little red segment in the otherwise white horizon, right?
I didn't even know she was a circle.
So the only way I would know is if I walked around her and I saw that from all directions she was the same, right? Okay. But you understand that even that is not strictly speaking the way they see it though, right? Because for us, we're going to see this white band, infinitely thin, right? That's the entire universe, but then that's going to be embedded in, like, there's going to be like maybe a blackness above and a blackness below, right? They don't have that though, right? They don't know about above and below. To them, that's everything. So we can't even see like they do, right? Does that make sense? For us, if we see a line, we perceive 2 dimensions. And so when we see a one-dimensional thing, it's always embedded in the 2 dimensions that we're perceiving, right? Now, a 4-dimensional creature would see it differently. They would be able to see things literally 3-dimensionally. They could see behind too then, right? They'd be able to, right? You get that? We can see left, right, up, down, and they're different. Something is either to the left of or the right of, and we can see that visually. Well, 4th-dimensional people could see front and back separately. You couldn't block somebody. Like TJ would never disappear. I would see him even now, but it would just be different. I don't know how, right? You get that? Okay, so understand the limitations. We can't even really immerse ourselves in their universe. We can kind of get an idea by doing this, right, and seeing that white band, right? But even then, we can't be flatlanders, right? Okay.
How did they test that? You said Einstein came up with the theory, so how did they test that?
Well, for one thing,
Yeah, that is.
the story I told you